Okay, so here we go. So I cannot see how I write over there, so maybe you're gonna have to help me over here. Oh, it's not gonna be that easy for me to write. So let's say here, this is ME304. Introduction to machine design. Okay, so let's go through some basic stuff. So basically, every time you need to do the design of a machine, you need to find the stresses. And the stresses will always be some type of function of whatever. We look at forces, moments. Let's say, let's think about this one will be what? It can be P over A, or this could be equal for the bending My over I, okay? Is forces divided by some type of the geometry properties of the cross section. Okay, so my experience is that generally you don't have that many problems with knowing how to apply the equations, but that from statics and solid mechanics, generally the place where you have the hardest the most problem to find is how to find the forces and the moments, for example, of beams. Yeah, go ahead. That better? Perfect. Yeah, no problem. So like I was saying, it's not that much about the geometry, because the geometry, you know how to find the moment of inertia and those things. It's not that complicated, or you can use some type of software. But generally, you have a problem in finding the forces and the moment. Basically, what I'm referring to is shear diagrams and bending moment diagrams. No? Okay. Generally, is where you have some issues at the beginning. So that's probably the first review I'm going to be doing. Okay. So if you want here, I'm going to do like quick review in shear. And bending moments. Diagram. Okay, so the first thing I'm going to do, I'm going to look at some basic equations. So some of the basic equations you probably use is, if I call the distributed load W, this would be equal to dV dx. I probably do a small figure now. Okay, so maybe let me just do the figure here. So let's say this will be the distributed load, and you will know that this will have a shear force, moment here, and M, okay? This is just for the explanation. And the other useful equation is that once you know distributed load, you can find the shear, or once you know the shear, you can find the bending moment by using either one of these equations. Okay. All right, so let me just put over here like a general procedure. Okay, that is something maybe, I don't know if it's specific about me, but it's about all my classes. If there's something that I'm picky and that I'm really trying to teach you is procedure. I don't care that much about final results, but I do care that you follow the right steps in order to get to the solution. So my belief is that anyone can do a mistake in an exam, but if you follow the right procedures, you're always going to get to an answer. And then you can go back to your answer and find what is your mistake, no? But if you always follow the same step in order to solve a problem, you will get better at it every single time. If you follow any type of procedure, different procedure every single time, it's just going to be different every single problem, no? Okay, so what would be the first step? What is the first thing you generally do in any problem in statics or solid mechanics? What is the first thing you did? There we go. Okay, so here, let's say I'm going to put here like a small problem, but to give us a hint about what needs to be done. Yeah, just do anything, okay? I'll put a pause here or whatever, just to give us an idea. So we do the free body diagram. This will not be the free body diagram. Our free body diagram should contain what? We replace this by the reactions, no? Oh, so maybe here we need to do something. So for example, if you have here a pin like this, what is this boundary condition called? Simply supported. So if you have simply supported, you can replace this boundary condition by what? Reaction on the X and Y. Perfect. Okay, what could be another boundary condition that like we have over here? Maybe that's what I'm doing here. What would be this boundary condition called? Can we call a roller? And if you need to replace this one, you will replace it by what? What's the difference between this one and this one? Yeah, so basically this one, we only have the Y, no? No X. And what could be the last one? Let's say will be this one here. Let's say I call it clamp. Sometimes they call it cantilever. So this time you need to replace this one by what? You need to replace it by a Y, by the reaction AX, AY, and a moment. A reacting moment. I mean, all this stuff is not that complicated. Just think for 1 second. If you have this and you apply a force, is this going to rotate when it's pinned? You have something pinned and you push, how is it going to move? This way, no? Yes. So this is going to be resisting in what? Only the X and Y, no? If you have a roller and you push, it's just going to react on the Y because it can slide on the X. So only on the X. Clamp, if you have something clamped but you try to move it, what's going to happen? It's going to resist moment, no? But also X and Y, no? So it's not really to memorize, it's basic understanding. Right? Maybe one thing here that I wasn't planning doing, but same writing, but I'm probably going to say it from this figure. From this figure here that I have, this one is simply supported, this one is a roller. So how many unknowns are we going to have out of our correct? So we're going to have 3 unknowns. What happens if I put here another simply supported? Correct. So basically we'll have 4 unknowns. So basically I just put 3 because the total number of unknowns we can have. So the problem is statically determined is 3 in 2 dimensions. Why is it 3? All right, so we have the summation of forces equal to 0 on the X and Y, and on the moment equation on the Z, no? coming in or outside the board, we can find the moment, no? So basically, probably every single problem you have in here will be statically determined, but sometimes I don't think we do statically indeterminate, okay? So all the problems will be solved will be statically determinate. So first thing will be to do the free body diagram, and really at that point, what you should say is say, okay, how many unknowns do you have? I have 3 unknowns. I'm going to need 3 equations. Okay. All right. So after the free body diagram, what should be step 2? What did you do in statics? Okay, so you need to find or solve for reactions. I'm going to put here forces, but it can also be moments, no? If it's clamp. So what are the 2 equations you're going to be using in order to do that? Summation of forces equal to 0, and summation of the moments equal to 0. Okay. 3, we get to the interesting part. Now is when you need to go and find for the shear let's say bending moment or bending moments equations. Let me just redo here that little figure that I did before. Okay, I mean, you can do a different figure, doesn't matter. I'm just trying to do the same one. Okay, so now conceptual question, and this is an important conceptual question. Okay, so you know probably Newton's first principle, second one. What is Newton's third principle? It's the one Johnny called a help you action reaction, no? If you push something, the object is going to push on the same direction with the same magnitude to oppose that initial force. Okay. So here I have a conceptual question is that when you write down summation of forces equal to 0 or summation of moments equal to 0, does that refer to any type of forces, just the external forces, or just the internal forces? Just the external, correct. So basically, and that's why you did something here. Why in here, you did it here over here, we did already. Why over here, we replace this simply supported by the 2 reactions? Conceptually, what are we doing? Correct, but conceptually, that's what we're trying to achieve. Conceptually, what we're doing is we're trying to replace this by 2 forces, no? So basically, if you look at this, the simply supported, this will be forces acting on it, and then it would be at the same time opposite forces acting at the contact of the beam with the support, no? But if we remove the support, now what happened? Those internal forces that are acting with each other become what? They become external. And why do we need those forces to become external? So that in step 2, we can apply Newton's equations. Okay? So Newton's equations are only valid for external forces, not for internal forces. So you need to make internal forces to become external. So here, basically, it's going to be the same thing. All right? What are here, let's say W, which is the distributed load, and P, let's say a local force. Those are external forces, but they're going to produce what? Inside the beam, they're going to produce internal forces that will be shear and bending moment. So in order to make the shear, internal force, and bending moment, external and internal force to become external, what do we need to do to that beam? we need to make cuts, no? All right. So what was the rule that you used? Johnny, you need to make a cut. You start from one end. You need to make a cut. Anytime is going to be a discontinuity in the loading. Yeah. Okay. So let's put over here. Let's say, and the idea is to make the internal forces to become external. Let's go over here. Make a cut. Every time there is a discontinuity in the loading. Okay, so basically you're gonna using the equation gonna find an expression for the x, okay, and with this one, I mean, you can either use this or you can use this method, okay? Generally, I use this one. I think it's more clear, but you can also use these equations, okay? This is more mathematical because you need to integrate, find constant of integration. This one is straight from the free-body diagram. Okay, so once you find the expression for the shear and bending moment or for other stuff, the last step would be to sketch shear and bending moment diagram. Okay, generally I like to make up problems to all my classes because I like to work with them from zero. But since I started recording, I find out that if I ask you to do the calculation, we waste too much time. So I took one over here. Let's see what this is. I brought one, so I have the results. So let me just copy it. But again, the idea is to do it without looking at it. We just look at the results. So let's see what we have over here. So basically here, one, I do a figure that would be X, B, X, M, okay? This is not correspond to this one, but let's say this could look like what? This way, this one generally will be, I have no idea how to be, but let's say, some type of figure like that, okay? All right, so let's do the example. So let's see, on this example, okay, it looks like I have here a beam that is simply supported at point A. It has a roller at point B and is free at point C. There's a distributed load of 6 kip per feet between A and B. So this is a distributed load. There is a punctual load at point C equal to 5 kip. And the distances between A and B is a foot, and between B and C, sorry, is 6 foot. So in here, what we need to do is to draw the shear. So let's say here, yeah, go ahead. Yeah, it's real. Yeah. So that wasn't a question, that was a request. But yeah, you can do it. Yeah, I mean, I don't really see from here. So, and as you can see, I need to stay all the way to this side. So it's not that comfortable for me to write, but so draw shear. And bending moments diagrams. So again, it's a review, but I don't start completely from zero. No, I assume that, you know, some stuff. So again, we're going to follow the procedure. So what is the first step? Free body diagram. So I don't write free body diagram, I write FBD, no? Okay. So now I do the same figure over here. So I just do a line. Oops. Here, okay, I put here point A. I put here point B, and I'm going to put over here point C. Okay, so what would I have at point A as reactions? All right, AX and AY. So I start with this. What would I have at point B? Rather, that would be BY. So here, if you want, starting about your head, how many unknowns we have? 3. Statically determined, we can solve it, no? Maybe we do some statically indeterminate, but so far for the review, no. Okay. Now, can I replace this distributed load by just one force? Okay, how do we do that? Okay, so we move it at the center. What would be the magnitude? 6 times 8. 6 times 8? 48, good. So this would be what? 48. But the unit would be 48. And let me put here if you want 6 times 8, 48. And it should be 48 kip. No, if you want, let's put it over here. And then the one at point C over here, we cannot replace it by anything. Let's say it will be 5 kip. All right. But again, and that distance over here, maybe we can put over here. I mean, it's too much. So this will be 4 feet. 4 feet. 6 feet. No. All right. So what is step 2? So for the reaction forces. So you see, this is basically statics, no? The first 2 steps. So, all right. So let's say, what are the 3 equations we can use? Let's be a bit dumb over here. Let's just go straight. So the first equation we can use is what? Summation of forces on the x. This will give us what? X equals 0. That I like because we have 3 equations. I like to put 1, 2, and 3. The first one is just going to give us that AX equal to 0. Then if we do summation of forces on the Y, this will give us what? AY plus BY minus 48 minus 5 equal to 0. Or from here, you would just get AY plus BY equal to 53. Would be equation 2. Okay, if you want me to be more accurate, since we do all the class notes, maybe here you should have put which coding system we're going to use. X, Y, okay, if you want. All right, specific. So now we cannot solve directly. We need to use the other equation. So what is the third equation we can use? Okay, correct. So when you do summation of moments, you need that equation like that doesn't mean nothing. When you take moments, you need to decide about which point. So here, what is the most convenient point? Really, you can think about any point, but which one is the most convenient? Probably A, because you get rid of two forces, no? Okay, but I mean, we know AX is 0 anyway, so A. What is the second thing you need to define when taking moments? The direction. So generally, what is the positive direction for moments? Is it counterclockwise? No, the default is counterclockwise positive. So I put it over here. If you don't decide, if you don't put it, I'm always going to assume that you're taking counterclockwise as positive. If you want to change it, you're going to have to show me, no? Okay. All right. So if we do this, what are we going to get? So let's see, we're going to get the 48. So AX, AY are going to do nothing. Then the 48 keep. We have 48 would be the force. What would be the arm? Would be 4 at the middle, no? So 48 times 4. Would that be positive or negative moment? That creates a clockwise moment, so that would be negative. What about BY? BY, we create a moment counterclockwise. So the force is BY, the arm is 8. And what about C? So the force is 5. We know make a clockwise moment. What is the total distance? 8 plus 6, 14. And this will be equal to 0. So let me look at now this note. So that, all right, so this will give you that 8 dy equal to 70 plus 192, which will give you that dy is equal to 262 divided by 8, or 32.75 kip. Okay, and now we can use from equation 2. We can find AY will be equal to what? 53 minus BY, which gives you AY equal to 20.25 kip. Okay. Oh, something nothing to do with this, but since I'm thinking about it, if you have assignments and you have problems with the assignment, you can ask in class, and sometimes I can work out the problem in class. Most of the time, I will do it with different data, but you have to redo it. But we can kind of work out problems in class as well, no? But then you will have to do calculations with me in class. All right. So, any questions so far? Let's see. All right. So now we get to the step that's a bit more tedious, which is step 3. Which is shear and bending moment equations. Okay, so let me redo a figure over here. We had A, B, C. And here we have a force P, but equal to 5. This was the distributed load here. Or is it going down, no? Yeah. Of 6 kip foot. And we know this was 8 feet and this 6 feet. All right, and here we can put X and Y. Okay, so we say on the procedure that you need to start from one end, it doesn't matter which one. And that the general rule is that you need to make a cut every time there is a discontinuity on the loading. So how many cuts do we need to do over here? So if you start here, is it going to be discontinuity on the loading between A and B? It's going to be discontinuity right at the time you get at B, no? So you need a cut. I'm going to make it in here, but you can do it anywhere, okay? So first cut, then we pass point B, and then it will be another discontinuity. Somewhere between B and C. Any question about this? How to find the cuts? Should not be new. You should have done that in statics and solid mechanics, no? All right. So we have the 2 cuts. So now, what do we make the cuts? So that those internal forces called shear and bending moment become external. And we can apply summation of forces and summation of moments. All right, so let's look at our first cut over here. First cut is between X equal to 0 and 8. So we don't get to 8 exactly, but and 8. All right, so now it just becomes a static problem over and over. We make the cut. What do we need to do? Pivot diagram. After pivot diagram, what do we do? Find the forces on the Y or the X and the bending moment. In order to do that, we do summation of forces and summation of moments. So again, it becomes the problem over and over again. So free body diagram. What will be the free body diagram in this case? So if I look at the, I make the cut over here. This is the cut. So if I look at the forces, I'm going to have here AY that we had was equal to what? AY 20.25. We knew that here I'm going to put it, but you don't need to put it just for the example. We found AX to be equal to 0. What else do we have over here? The distributed load, if one is W equal to 6 kip per feet. I was going to do it in red, but probably I'm going to do it in blue. And the most important thing that we have is what? Now that we make the cut, what's going to happen? A shear force and a bending moment, no? M1. So now, and again, if you want, we can put here X. I'm going to put here X just to help you. All right, now, in order to find the shear V1, what is the equation we need to apply? Well, in order to do here, let's say shear. We're going to apply which equation? Summation of forces in which direction? I mean, you can do on the X, but the X is nothing in this one, no? So we do on the Y. And now, so what do you have on the Y? I will change the values. I just do it symbolic now, but it will be AY minus 6 what? 6 what? 6x, perfect. This is distributed load. What else we have here? Minus V1 equal to 0. So this will mean what? That V1 in function of X, if you want, this is not multiply, okay? Let's remove the X. Let's just say V1, to make it easier, will be equal to what? Will be equal to minus 6x plus AY, or this will mean that V1 will be equal to minus 6x plus 20.25. Okay, so you can do that later, but let's do it now. Since I have the information, we're going to need that later on to plot it. So V1 of 0 will be equal to what? 20.25. And this is a linear function with what? Negative slope, no? Minus 6. So V1 at what would be the end? What should be the maximum value for X? Is 8. So if you substitute into by 8, you have minus 48 plus 20.75. This should give you minus 27.25. Now, in order to find the moment, the bending moment, what is the equation we're going to use? Summation of moments, but here you need to be careful because here you don't really have the choice. I mean, you have the choice, but this is the simplest way. Just use always the same point about which you're going to take the moments. What would be that point? Always take it about the cut. It makes life a lot easier. Yeah, I mean, I'm sure that's the way you have done it. Again, I like that you specified the direction of the moment. So this should be equal to 0. So this will give you what? But if you look at the figure, you see everything comes from the figure. So what is creating a moment about the cut? Let's look at the AY force. Is that creating a positive or negative moment? The AY. Negative. What is the arm? X. Perfect. Now, what about the distributed load? Is that creating a clockwise or counterclockwise? Counterclockwise, so that would be plus. What would be the magnitude of the force? Okay, Cx is the value of the force. And if you take the force and substitute it, where are you going to substitute it? In the middle, no? Like you did before. So the value of the force will be 6x. And what will be the location? X over 2. Again, this should not be new. All right, and the most important one, now we have M1. So you need to do it now. What plus M1 equal to 0. So this should give you what? M1 should be equal to minus three x squared. AY is equal to 20.25, so plus 20.25x. Okay, over here I'm going to put, but this is not linear, this is quadratic. So, I mean, let's just put it, we do that afterwards. So let's say M1 of 0 will be equal to 0 the moment. And M1 at 0.8 is equal to minus 30. Maybe we can do it now. Let's do it when we do the figure. I think it will be easier. It will make more sense. Okay, any question about this first cut? We got the first two equations. Now we go, and we're going to do something similar for the second cut. So, second cut, this time, this one is between x to 8 and 14, no? Okay, so same as before, what is the first thing you need to do? Some type of Fibonacci diagram. So your Fibonacci diagram now, we are past the 0.8, so you can keep here the distributed load. How much was it? 6 keep it. So this is point A, this will be point B. All right. So we have here the Y, AX, we have PY. So AY is equal to 20.25. BY is equal to 32.75. What else do we need over here? The internal forces, so the internal shear, V2 and M2. Okay, so again, to find the shear, what is the equation we're going to use? Summation of forces on the Y. That will give us what? So I'm going to put here AY plus BY minus what? Minus 48, that will be the 6 times 8 now, this one that we can replace over here. What else I'm missing here? Probably the most important thing. Minus V2 equal to 0. So this is basically going to give you V2 equal to 20.25 plus 32.75 minus 48. Which gives you a value for V2 of 5. So that means over here that the shear force will be constant between 8 and 14, no? I mean, at least on that cup. All right, next we need to find the bending moment. In order to find the bending moment, what do? Take the moment about the cut. All right, so let's start by the moment about the cut. So let's start maybe by the force AY. Will AY be creating a positive or negative moment? Negative, so we have what? Negative AY. What will be the arm? X. Perfect. Now let's do the same thing since we're doing first AY. Let's start with BY. BY will create a negative or a positive or negative moment. And as AY, no, same direction, will be creating a clockwise moment. BY is the value of the force. What will be the value of the arm? Will be that distance over here, no? Yeah. It will be X. X starts from here. It will be X minus 8. Okay, so we took care of AY and BY. Now we need to take care of the 6 kip distributed force. So that one will be creating a positive or negative moment. Positive, so what would be the value of this one? What is the value of the force? 48. What would be the value of the arm? What is that distance from here to here? This is 4 feet, and here this would be 4 feet. So what would that be? X minus 4, no? Okay, so we have this, and let's not forget the most important, which is one. I don't know if this is the most important, but the one we need to find, which is M2. So basically here we find M2. So we get, all right, so I want to put the values here. So it would be, move everything to the side would be, so 20.25 X plus 32.75 X minus 8 minus 48 X minus 4. So let me look at if you do the algebra, this should give you pretty simple. M2 of X equal to 5X minus 70. Okay, so you see this is linear. This will give you what? M2 at 8, because this time we start from point 8. This should give you 8 times 5 is 40, so minus 30. And M2 at 14, that one we'll have to look at. Even though 14 times 5 would be 70. Yeah, so 70 is 0. Okay. All right, so looks like we got everything here, no? All right, so we go to step 4. Shear and then the moments diagram. Okay, so before we do the figure, let's try to recall the equation. So we have V1 equal to minus 6x plus 20.25. And we know that V1 of 0 equal 20.25. V1 of 8 equal to minus 27.25. V2 is equal to 5. So that one's going to be that should be pretty easy to sketch. 52, yeah, should be pretty easy. Okay, but since we go to 20.25 to minus 27.27, that means that it's going to intersect the x-axis. So, okay, how can we find the intersection point? I mean, we don't need to take no need to. Basically, what would be V1 and the intersection? Okay. The section point with x-axis. This means V1 equals 0, so this means that minus 6x plus 20.25 will be equal to x, so the intersection point will be x equal to 20.25 divided by 6, which is equal to 3. Yeah, I was getting too comfortable for me. I mean, I have this here, but yeah, thank God. So 3.375. If you want, you can probably give a fit, okay? All right, so now we got everything to do the shear, but let's look first at the moment one. Now, if we look at the moments, we had M1 equal to minus 3x squared plus 20.25x, for which we know that M1 of 0 is equal to 0, and M1 of 8 negative 30. Okay, so this one we see is kind of a quadratic. So probably we need to find what would be the location of the extremum, no? Even though, do we already know that or not? I mean, let's just do it if you want, since we have time. So how will you find the extremum? Correct. But that's because why? So generally, what would be the general way to do the extremum? You will do dm dx and solve for x, no? But recalling that the equation we are at the beginning is what? What is v? V is dm dx, no? I mean, if you want, you can redo the operation, but didn't we just solve the point where v was equal to 0? Yes? Okay. So here, v equal to 0 when what? X equal to 3.375, no? Yeah. I mean, you can redo it, but you're going to find the same thing. Okay, so really what we can do here is that let's say M1, I don't know to put this, max to be equal to M1 at 3.375. So if you substitute into M1, let's see by any chance I have that value. I think I have it, 34.70. Okay, so if we do the diagrams, one, and a half. X, D, M, X. So I say it would be 0, 0. What were the points we had? This would be, let's say, 8. And let's say this would be here 14, no? So if we look at our figure, go a little bit to the left. What do we have? V0 equal to 20.25. So let's say we go from 20.25 to what would be the value over here? Minus 27.25, no? And this should go on a straight line. So probably I'm much better than me doing a straight line. Straight line is nothing but straight. What is the value of this pointer here? 3.375 was the intersection point. All right, so this is between 0 and 8. And what do we have? There is a jump between 8 and 14, and we know that V2 between 8 and 14 is equal to what? 5. So this should be the figure diagram. Sometimes I do this stuff so you see what it is. All right. Now, what do we know about the moments? M1 equal to 0, so we start from here, and M2 equal to minus 30. So let's say we go here to minus 30. So we know it's going to go up this, oops, yeah, it's going to go up this way. If you want, you can calculate which point is going to intersect, but I wouldn't go that much. I go here. You know, it's minus 30. Now, what do we know about? Oh, I didn't put it here. Sorry for that, guys. We have M1. Maybe I should put it here. All right, it's not going to look pretty, but I forgot to put here M2. Sorry for that. M2 was equal to what? 5x minus 70. And we know that M2 of 8 was equal to minus 30. And M2 of 14 equal to 0, which is what is expected, no? So let's see. We have minus 30, so which is good. And we go to 0, and we know this is a straight line. Once again, this will be the bending moment. Okay, so last thing, have you copied this or do you need more time? All good? All right, so if we have this, why is this important? So for example, let's say now you need to find maximum bending stress. What is the expression for bending stress? Is my over I, no? So what will be the location of the maximum stress? Okay, so located at x equal 3.375, for which M max we found to be equal to, I think I put it here, but I didn't put it on the figure, 34.17. Okay, and let's say we wanted to find the maximum shear stress. What would be the expression for this one? That's the one also that you don't like, generally, is VQ divided by IT. But again, this will be located where? Will be at x equal 8, correct? And D max will be equal to what? 27.25. So now that we know how to find the location of maximum bending, maximum shear, we need to start dealing with the, maybe find the properties, no? What would be the I? What would be the I? You don't have any problem, generally. The Q, you don't like it. Okay. And so on. So that would be it for today. Any questions? So probably what I'm going to give you, when I give you the heads up, is we don't have computers in class, but probably I'll give you an assignment about shear bending moment diagrams, and I'll provide you a little video that you don't have to use it, but it can help you to check your answer about how to do this to find the shear bending moment diagram in Nastran. So using finite element, you can put it into your finite model, and it will give you the shear bending moment diagram. That way, you can check if your work is correct or not, no? All right. last thing is we have 1 minute. Does it, here's an example, but can the bending moment diagram be discontinuous? By meaning discontinuous, can it have a jump over here or anywhere? It cannot, because maybe you study that, you don't always study this stuff. Is that generally, how do you determine the deflection? Deflection generally is given by m of x divided by ei, and you integrate. So basically, if you want, the deformation is related to the bending moment. Can the deformation not be continuous? The formation of an object needs to be continuous, no? Yeah, if it's not continuous, it means that it has some type of a break. Okay.
But in solids, we would have like point moments, and in our bending, like shear force diagrams.
But that would, but the point moment would not change the deformation; they would change the rotation, the twist. Sense? Okay. All right. All right. So see you next week.